So this chapter is on thermodynamics. It's the first of two chapters on the subject. The first one you learn in first semester general chemistry, and then the second chapter comes up in second semester general chemistry. So the first semester deals with energy and enthalpy. The second semester deals with entropy and free energy. So by the time you get through all that in the second semester, you've got a pretty good understanding of thermodynamics or thermochemistry. And chapter 6 is listed here, but it's different in different books, so just go with whatever it is that your book is using. We talked about different types of energy, potential and kinetic energy, and then internal energy has to do with molecules that are moving with kinetic and potential energy. I mentioned translational energy, which is just the kinetic energy of the molecules moving around in space. Then there's vibrational energy, rotational energy, electronic energy, all these different types of energies that molecules can have, and add it all up, and that's called the internal energy, given the symbol E. So also we discussed a system of, I believe it was a beaker with some water in it, excuse me, and the system would be considered the water. The surroundings is going to be everything, the air above, everything outside the system, like this, and see, the water here would be the system. So then the universe, according to a thermodynamic definition, is that it is the sum of the system and the surroundings. That's important in thermodynamics because sometimes we calculate heats or entropies associated with the surroundings and compare those to the system, and you can learn a lot if you add them together to say something about the universe. All right, temperature is a measure of kinetic energy of the molecules when they're in physical contact with a thermometer, and the molecules collide, transfer. It's an equilibrium process between the kinetic energy of the molecules and the energy of the mercury in the thermometer. That's one way to think about it. There's an equilibrium, and when the system comes to equilibrium, then the mercury rises up to a certain level. We read the temperature associated with that kinetic energy. Heat, on the other hand, is energy transferred across the boundary of the system. That's a pretty important definition there for thermodynamics. And we use the terms exothermic and endothermic to talk about whether heat's given off by the system or heat is absorbed by the system here. And we can use these two symbols, delta E and delta H, to indicate the heat, and it just depends on the conditions under which the heat was measured. If it happens to be a constant volume system, it's something that's a closed system, it's got a cover on it, some heat change can be measured by looking at temperature, for example, and that heat change Q will be equal to delta E. On the other hand, if you have an open system like water in the beaker, it's open to the air, the atmospheric pressure, and the heat associated with some process being chemical process carried out in the beaker would be referred to as delta H. So constant pressure conditions versus constant volume conditions. Don't worry about it. I don't emphasize this at all for this chapter. The numerical difference between these two values is very small, and we're just going to say delta H equals delta E, which is Q. Okay, so here the reaction. This reaction is methane plus O2 forming CO2 and water. We know this to be an exothermic reaction, so Q would be equal to 890 kilojoules, but notice the negative sign here is indicating that heat's given off. One way to indicate the heat would be to put it in a separate line. Another way to do it would be to actually incorporate it into the chemical equation. When we do this, this then is referred to as a thermochemical reaction where the heat is included. If it's exothermic, the heat will be on the right-hand side of the thermochemical equation. If it's endothermic, a positive sign, if we did it this way, we would put it on the left-hand side. So 890 kilojoules carried out under constant pressure conditions, delta H under constant, this is a typo here, this should say volume. Not that it matters because we're going to ignore it anyway, but to be technically correct, it would be delta E. So again, these numbers are the same, so we're just going to call it Q, or lots of times we just call it delta H. All right, I think I just said that. Don't worry about the surroundings. I'm not going to talk about it, although your book does. And this is the actual relationship between delta H and delta E. This part right here is very small, especially for things we're going to look at in this course. Okay, so instead I focus on heating or cooling a substance, phase transitions, and reactions. So we'll look at each one of those in detail. These two taken together, and then this is a separate topic. So this is referred to as a heating curve. I don't know why you'd call that a curve, but that's what it's called. Heating curve, and then the next slide it's the cooling curve. And this used to be in chapter 11. I have, let's see. It used to be chapter 11, page 489. I'm guessing that's probably the 3rd or the 4th edition of TRO. And now we're using the 5th edition. It's in chapter 12, page 524 for the 5th edition. But if you can't find it, just look up heating curve for water. So just to describe it here, you start at very low temperatures, and also I like to make another change since I stole this from the internet here. Change this to heat added. Not exactly the way I wanted it, but it was pretty good. Okay, so you start with a solid material at low temperature and start adding heat to it. As you add heat, this temperature of that solid is going to increase. So this region right here is just heating, warming up the solid. When we finally get the system up to the temperature, the melting temperature or the melting point, then you continue to add heat, and now that solid's going to melt. The temperature stays the same during this process. Then, once it's completely converted to liquid, continue to heat it, and the liquid heats up. If it's water, it goes from 0 degrees C all the way up to 100 degrees C. When it hits 100 degrees C, then the liquid's going to boil. This is an example of a phase transition. This is an example of a phase transition where the system goes from, in this case, solid to liquid. This time it's liquid going to vapor, or you could put G there for gas if you wanted to do that. Then keep heating until all of the liquid has become vapor. Continue to add heat, and then the gas just heats up. So these 3 regions are just associated with heating, and then the 2 horizontal regions are associated with phase transitions, liquid to solid and solid to liquid and liquid to vapor. So we'll look at equations for all 5 parts of this graph, and we'll see the green, just the heating. These regions have equations in common, but there are some differences as well. Now, corresponds to the heating of the solid. We had solid gold, right? In the case of water, it was liquid. That part doesn't matter. It's just that the equation Q equals MC delta T is what you need for these regions. And then the next topic, which I just toggled to on the slides, has to do with the phase transitions. And there's another one. So, where was I? We have on the next slide a cooling graph or curve, and you basically take your gas and maybe put it in the refrigerator. So heat is being removed from the system, and when that happens, the temperature is going to be going down. So this is a cooling process here. Next step is the phase transition. This is going to be vapor going to liquid. So that's the phase transition there. Then another cooling process. You just keep sticking it in the fridge or freezer, and heat's being removed, temperature's dropping. So this is just the temperature change here. Then the phase transition, liquid to solid. And finally, when you have the solid, it's going to cool down again. Okay. So what equations are we going to use? So for the heating and the cooling parts of this, we have this equation, Q is equal to MC delta T. You must know this. You must have seen this before. I think in high school, sometimes they use the symbol S, MS delta T. But anyway, it stands for the heat capacity or the specific heat. The notation here is you're looking at S's versus M, and also the term specific heat capacity versus the term specific heat, and then the molar heat capacity. So how do you keep it all straight? The specific heat capacity is the heat needed to raise or lower the temperature of 1 gram of substance by 1 degree C. I don't have this written down, but the specific heat refers to water. So it would be the heat needed to raise the temperature of 1 gram of water by 1 degree C. And it happens to be 4.184 joules. And then the molar heat capacity, CM, definition similar. The heat required to raise or lower the temperature of 1 mole of substance versus 1 gram of substance. And then both are by 1 degree. So you use, if you're using specific heat capacity and you're talking about the heat needed to raise 1 gram of a substance, then you're going to use M for mass in grams, and then this would be per gram, specific heat per gram. If you have moles of substance instead, you can use M, that's the symbol for mole or molar, and then this would be times the number of moles. That's the difference between the two. And it's very interesting to look at this table. And 4.184 is the number for water. That's the number of joules needed to raise 1 gram of substance by 1 degree. And if you compare water to all the other substances in the table, you see that it's much, much higher. So it takes way more heat to raise the temperature of water than the other substances. And that has to do with their hydrogen bonds. And we haven't studied hydrogen bonds yet, but we will. Hydrogen bonds are very strong. That's the interaction between the molecules. So the energy added has to break that interaction before the molecules, let's say, go into the vapor phase. And so it just takes many more joules to do that. Metals, on the other hand, we have 0.1, 0.2, 0.3, 0.4, joules. So big difference there. And also you have sand, that's interesting, 0.84, granite, 0.79, and glass too. You can think about the weather in this example, and in California we have the weather at the ocean, and then we could consider the weather in the desert, right? So on the same day, if you're at the ocean, from morning to night, the temperature doesn't change very much, as opposed to the desert, where it's very cold at night and then can get very hot during the day. And the difference between them is the water vapor that's present in the air. So at the ocean, there's lots of water vapor in the air, and the temperature of the air doesn't go up or down so much because all of the energy is needed just to break the hydrogen bonds in water molecules, as opposed to the desert where the water vapor is very low and the heat just heats up everything else in the air, the nitrogen and the oxygen and so on. That's a good example there. Okay, so I wanted to do this calculation. This is just to get used to working with the different units and the different definitions. Let's first look at the heat needed, that's Q, to raise the temperature of 15 grams of water from 20 degrees C to 50 degrees C. Then we're going to look at gold, same mass, 15 grams, same temperature change, 30 degrees. The only difference is the substance. So I want to calculate Q for both of those. Let me find that. So there's 15 grams of water, and delta T is equal to 50 degrees C minus 20, back up there, 20 degrees C, and that's going to be 30 degrees C. And since it's water, we're going to use the symbol CS, and that is equal to 4.184 joules per gram degree C. Put the little degree in there if you want. Don't have to. And put it all together, we're using the equation Q is equal to MCS delta T. And of course, this is going to be equal to delta H. Or delta E. But this is the equation here that you're probably familiar with. So put it all together, Q is equal to 15 grams times 4.184 joules per gram degrees C, and delta T is 30 degrees C. Q turns out to be 1880 joules, which is equal to 1.88 kilojoules. So before we move on to the gold calculation, let's go ahead and use the molar heat capacity for water. I'll put it on the top there, put it in red there. So the other symbol is Cm, molar heat capacity, and the value for that is 75.4 joules per mole degree C. Joules per gram degree C versus joules per mole degree C. So here, delta H will be equal to Q, which will be equal to M, the number of moles, times the molar heat capacity, times delta T. And we want to take our 15 grams of water, convert to moles using molar mass, 18.02 grams per mole water. Now we have the number of moles. Multiply it times 75.4 joules per mole degree C. And then delta T is the same, 30 degrees C. and calculate that. We're going to get the same answer, 1880 joules, which is 1.88 kilojoules. All right, now we want to do a similar calculation for gold. That's the second example there. And using gold, and we have molar heat capacity for gold as 25.21 joules per mole. Could be per Kelvin or per mole. The difference between Kelvin is equal to the difference between moles. But I want to use degrees C to be consistent there. Okay, and for this one, you still have 15 grams, and also delta T is 30 degrees C. So everything's the same, except the mass is the same, the temperature change is the same, but the material is different. So Q, that's equal to delta H. Q is equal to N times Cm delta T. Q is equal to 15 grams times, well, we got to get rid of the grams and go to moles. So use molar mass 190, 6.97 grams gold per mole of gold. Then, so now we have moles, and now we're going to use specific heat, molar heat capacity 25.21 joules per mole degrees C, and then delta T 30 degrees C, and Q equals 57 joules. So compare 57 joules for gold to 1,880 joules for water. Same mass, same temperature change, but quite a bit more heat is needed to raise the temperature of water than gold. And again, it has to do with hydrogen bonding. All right, that's a very interesting example. Next, we have just calculated here corresponds the phase transition. Well, let me back up and say that the heat that, so here are the phase transitions, this horizontal part of that graph. And there's actually 6 different phase transitions. Some of them you don't think about so often. Heat of fusion. Fusion is the same thing as melting. And you have heat of fusion here. You can also see this sometimes as delta HF, fusion. And you just have to remember that means melting. Then this is a symbol for heat of vaporization. And notice what this is. It's the heat needed to take 1 mole of the substance through the phase transition. So sublimation is going to be the one where it goes from solid to vapor. Okay. Fusion is going to be solid to liquid. Vaporization is liquid to gas or vapor, right? And then with condensation, it's the opposite. So condensation then is associated with the gas or the vapor condensing into the liquid phase. Heat of crystallization would be the liquid going to the solid phase. And then deposition is the opposite of this one. The opposite of sublimation is deposition. So deposition is really interesting. This is going to be the gas or the vapor going to solid. And I have had some experience with that in the lab. We sometimes make these solid materials from the gas. It's a situation where there's a substrate that's very cold. In my case, my temperatures were 77 degrees Kelvin. And under a vacuum, you'd introduce some molecule or some atom, in fact it was argon, mixed with some substance I wanted to study, and spray that onto the solid, and it goes to the crystalline state or the solid state immediately, and then you can study that spectroscopically and look at molecules that are isolated from one another in kind of a matrix of argon. It was kind of fun. I did research in that field for quite a while. Anyway, I kind of made up these. Some of these are just my own symbols, but as long as you define it, it's fine. Your book might have slightly different symbols for this, but anyway, we're just looking at the process here. All right, so here is a calculation for the horizontal part of the heating curve, and the calculation here is what is the heat needed to melt 0.5 moles of ice. And the heating is easier than the phase transitions has an easier equation than the heating. So this is for the phase transition, and we're going to use the equation that, delta H of fusion is 602 kilojoules per mole. So you could use that number if you had 1 mole, but if you don't have a mole, in this case you have half a mole, then we've got delta H for the process, which is going to be equal to Q, and this is N times delta H for the transition, whatever the transition is. So delta H for that transition is heat for that transition, and it's just the number of moles times it. So in our case, we have Q is equal to half a mole times the heat of the transition, which is 6.02 kilojoules per mole. So it's just half of that. So it's got 3.01 kilojoules. Whoops. Kilojoules. All right, easy enough. Easy, but this is the hard one. This big problem here is also in a different chapter. I believe it's going to be chapter 12 again for the 5th edition of TRO. You can look that up. I call it the big problem. Nobody else does, but you're going to take that heating curve, that diagram that I showed earlier, and now you're going to just calculate for every step. So, in other words, you start with H2O at minus 5 degrees C. Then you raise the temperature up to 0 degrees C, and it's going to go through, so this is heating here, right? When it gets to 0 degrees C, you're going to get the phase transition, and you just add heat during that process. Then it'll start to heat up again, and it'll go up to 100 degrees C. And then at 100 degrees C, you get the next phase transition. And then in this particular example, we're going up to 110. So in other words, we're starting here at -5, and we're raising it up to 110. And we can look at the heating of the solid, the heating of the liquid, the heating of the vapor using Q equals mc delta T. Then we can look at the phase transitions for this one, solid to liquid, and this one, liquid to vapor. And you can think of this in steps. So step 1, step 2, step 3, step 4, and step 5. You can calculate the heat for each one of the steps, and then add them all up to get the total heat. So calculate the heat needed to raise the temperature. Of course, it's going to go through the phase transitions, but that's the idea. Okay, so let's see if I can move this. Yeah, okay. So I'll do it right here. And we'll start with step 1. And we're going to heat the solid from -5 degrees C to 0 degrees C. So we have delta T is 0 minus a -5. So that's equal to 5 degrees C. And we're going to use Q is equal to M. Hold on now. Okay, there's more information. Oh no, we have it right here. So we're given the information here that the specific heat of ice is 2, specific heat of liquid water is the one I was talking about, 4.184, and then for the gas phase or the vapor, it's going to be around 2 again. So you get these 3 different numbers, and also you have different heats for the transitions for melting and vaporization. We're going to use all of those. All right, so we start out with our solid. So we have specific heat as 2.09, and let me move this down a little bit. Okay, I think we're ready. So Q will be equal to half a mole times 18.02 grams per mole. So you convert moles to grams first. So that's M, and then we have C, which is going to be 2.09 joules per gram degree C. So MC, and then delta T in this case is going to be 5 degrees C. And the answer is 94.2 joules. All right, that's for step 1. The next step is 2. This is going to be the solid to liquid phase transition. And for this one, we have Q is N times the heat of fusion or melting. So we have 0.5 moles, and you put some zeros. I'm not too worried about the sig figs here. 6.02, and that is kilojoules per mole. Now for these, it's important to have the same units. For the phase transitions, you're going to have kilojoules. For the regular heating, it's going to be joules. So let's go ahead and multiply times 1,000 here. Joules per kilojoule, just to have it all in joules. So in joules, you have 3010 joules, or 3.01 times 10 to the third joules. The next step is to take the liquid. So we're going to heat the liquid from 0 degrees C to 100 degrees C. And then delta T here will be 100 minus 0, so it's going to be 100 degrees C. So this is similar to the calculation for part 1. Q is 0.5 moles times 18.02 grams per mole. We're using specific heat of water, 4.184 joules per joules per gram degree C. And delta T is 100 degrees C. And Q for this one is equal to 3770 joules. And notice how much larger that is than the solid to the liquid transition in part 1. First of all, the temperature change is larger, but also the heat capacity is larger, or the specific heat is double, right? Part 4, we are looking at the liquid to vapor or gas phase transition. And we're going to say Q is equal to 0.50 moles times, let's see, we have 40 for that phase transition. We just used 6.02 over here for the solid to liquid. Now we're going to use 40 for the liquid to vapor transition. Okay, and so this is times 40.7 kilojoules per mole. So this turns out to be, and also that's kilojoules. So let's go to joules, 10 to the third joules per kilojoule. So for this one, this is number 4. This is 20,300, which is 2.03 times 10 to the 4th joules. All right, then the last one, number 5, is number 5. And we're going to heat the vapor or the gas from 100 degrees C to, I believe it's 110, 110 degrees C. And so delta T for this is 110 minus 100, which is 10 degrees C. All right, then we're going to use Q is M. That's the mass. C, you have to go to C for vapor. So it's going to be 2, is that right? Yeah, 2 point. Don't want to get them mixed up here. Heating the vapor. Yeah, last time we had 4.184. Now we're going to use 2.01. 2.01 joules per gram degrees C. And Q for that one, that's already in joules. That is equal to 181.1 joules. All right, now you want to add them all up. You're going to add up for the heat for part 5, you just add each one. Part 4, part 3, part 2, and part 1. So you're going to add them up, and you're going to say Q total is equal to Q1 plus Q2 plus Q3 plus Q4 plus Q5. There's no shortcuts with this one, by the way. You can't just multiply times the overall temperature change, 110 degrees minus a -5, and use that in anything. You have to do every step, and you have to consider the temperature change for each step. There's no shortcuts at all on this one. Takes a while to do it. Imagine it being a 20-point problem on an exam. And this ends up being, if I got this right, 27,400 joules, which is 27.4 kilojoules, or 2.74 times 10 to the 4th joules. But this is good right here. 27.4 kilojoules for the whole thing. All right, that's the end of this first set of slides for thermo, and we'll pick up on the other side for the second part.